Thank you for attending this presentation, and I'd like to thank Black Hat for the opportunity to present our work here. Now, before we begin, I'd like to know just how many of you are actually familiar with the second version of the HTTP protocol? If you could raise your hand. Okay. Second question, how many of you have actually got to implement it as part of, I don't know, you had to write a client or software? Thank you. And one last question is, how many of you have actually done passive client fingerprinting or any sort of client fingerprinting? Okay, thank you. So this is the agendas for today's presentation. I'm going to walk you through some of it. We're going to look at the research data and how we gathered it for this HTTP2 research. Then I'm going to do a quick overview of the HTTP2 protocol, by the end of which I hope all of you would be quite familiar with the key elements of the protocol, especially the ones we've used for the fingerprinting, and the key differences between the second version of the protocol and the prior versions. Once we've established that, we're going to go through the concept of passive client fingerprinting, and more specifically, how we propose to do it on the HTTP2 protocol. And last but not least, the bonus slide of the threat landscape we will cover for. So just a little bit about me. I work at Akamai, and I fairly enjoy big data and single malt whiskeys. So if you got any or you want to take some after the presentation, I'd be happy to meet with you. Some acknowledgements are due. This presentation is based on a white paper that we've published a few months ago, and I invite you to go search it and read the full white paper. The research was led by two other researchers, Ori Segal, which is the director and manager of the threat research team, and by another security researcher called Aaron Friedman. So acknowledgements to them. So let's talk about some data collections. This is the research data corpus for this white paper, for the work we've done. We've actually looked at 10 million different HTTP2 connections, and I'll explain shortly what HTTP2 connection mean. And we reviewed more than 40,000 unique user agents, which cover hundreds of different HTTP2 implementations. The data was covered, the data was grouped from Akamai's intelligent platform. For those of you who do not know Akamai is a leading CDN. And we have a very deployed network, 220,000 edge servers, which are deployed worldwide in 129 countries. We are essentially 90% away, one hop away from 90% of the internet users. And we actually provide the content for some of the biggest hosts and websites in the world, and we estimate that we deliver about 15 to 30% of all the web traffic. So this is the platform that was used to gathering this data. So I think it's a fairly, it's a fair sample that would show what is going on in the real world. When we get to the threat landscape, one of the things that we do analyze and collect on this platform is web attacks, and we see a lot of those attempts. So that was used for depicting the Lang threatscape as well. Some statistics about H2 that we see on the platform. I know that from time to time there are some adoption rate statistics in the internet. The latest one that I've seen are from, I think, September, and they are talking about 17% of H2 adoption, which is quite high. We currently see on our platform about 1 billion requests per day, and we see 27 million IPs using HTTP2, and more than 15,000 hosts supporting that. That's a lot of numbers. Overall, you can say that 10% of the entire traffic going on the platform is on H2, and you should keep that in mind and correlate it with the numbers of 17% adoption rate that is published in various sites. So let's do a deep dive into the H2 and overview of the protocol. I would start with a simple HTTP1 request and would have you keep it in mind. For those of you who doesn't know HTTP, this is a simple request. This is a text protocol. Version 1 and 1.1 of the protocol was a text protocol. First line, we get the method, the resource. In this case, it's a get method to index HTML. We have the protocol version and some of the hosts that depict information about this request. Keep that in mind, and let's start doing the HTTP2 overview. HTTP2 is based on a protocol called Speedy that was developed by Google, and it was actually formalized late 2015 in two RFCs, one dealing with the actual protocol, and the second one is dealing with a header compression mechanism called HPAC. Now, as opposed to the version 1 and 1.1 of the protocol, this is a binary protocol, and we'll see what does that mean later on. It can be submitted either over clear text or over an encrypted channel, though I have not seen up until today a single implementation which is being transmitted over TCP clear text. All of the implementations that we've witnessed are using TLS. And last but not least, its purpose is to address some of the challenges, mainly around performance, that prior versions of the protocol did have. So what are the challenges? The first one is concurrency. In order to achieve concurrency in the first versions of the protocol, you had to do multiple TCP connections. Can anybody think why is that not such a good idea in terms of performance? Well, TCP has a mechanism called slow start. It's part of its flow control mechanism where it starts very slow and exponentially brings up the pace until it's at the sending rate until it encounters the first loss. And if you do multiple TCP connections and you keep opening those TCP connections and closing them, you are actually getting a performance hit by the slow start mechanism of TCP. In version 1.1, 1.0 of the HTTP protocol, you can have only one standing request on each TCP connection. In version 1.1, a new mechanism was introduced called request pipelining, where you could actually pipeline several requests on the same TCP connection. But the downside is that if you had one big request or one big response, there was a head of line blocking. It wasn't so efficient. The second challenge here is the header compression. As you've all seen in the slide about the first request in HTTP 1, the headers are very verbose and they tend to be very repetitive. Some of the headers go back and forth in each request or in each response, and this is an ideal ground for compression. And no such compression mechanism was introduced for the headers in prior versions of the protocol. Last but not least, the passive server concept. In H1, actually the server could not initiate any sending of data to the client without having the client first request that data. And you might wonder, why is that important? Why should the server want to proactively send data? Where there are a lot of situations in which the server can know ahead of time in a very high level of probability that the client is going to ask for several resources. The classic example is when you download the main page, HTML page, and the client starts to parse it, and it's quite obvious that the next step is going to generate more requests for the static content, for the CSS and the JavaScript file. If we could have the server send those files to him with the initial request, we could save a lot of time. And as I've said, these are performance hits that the second version of the protocol is trying to actually address. So in terms of concurrency, we no longer have multiple TCP connection. HTTP 2 uses a single TCP connection, and everything is multiplex on this connection. For compression, we now have HPAC, the second RFC that was published along with the RFC for the protocol, which now compresses the headers, and that is much more efficient. And a new concept for server push was introduced in this new protocol. And if any of you is feeling uncomfortable with the fact that the server could be proactive, there is a way for the client to opt out of it at the beginning of the connection and say, not interested in you pushing me anything. Okay, so we have a single TCP connection in which the data flows, and that connection is divided into logical conversations, or we can group it into some kind of conversations called streams. These streams are numbered going from 0 and up, where essentially even numbered strings are, according to the RFC, are streams that were initiated by the server, and odd numbered streams are initiated by the client. Stream 0 is the only stream which is dealing with the parameters for the entire connections, and we'll see that later. So this is the definition of a stream according to the RFC. It's an independent bidirectional sequence of frames exchanged between the client and the server. So now we are going to see the most important unit of communication in the H2 protocol, and that's the frames. And each frame which is going over the wire between the two peers is allocated to a certain stream. In this case, it's stream 93. And these frames are actually the basic unit of communication in this protocol. Now, just as a HTTP message in version 1 protocol could have two sections, a header section and the actual body of the message, or it could have only a single section, a GET request with nothing in the body would only have headers. So we group streams which are logically can be mapped into requests or responses. And for example, a request could have a headers frame and a data frame, just as a regular HTTP message would have them. I don't know why you're seeing them as white, but okay. So these are the key elements. We've spoken about frames and we'll elaborate about them shortly. And we have spoken about streams, and we've mentioned that each stream should have a unique stream ID and it could have a priority set to him. And a message would be a sequence of frame which would be logically mapped into requests or responses. So let's talk about frames. This is the most important unit in the protocol. The RFC defines 10 types of frames, and they can be mapped into 3 logical groups. First of all, the frames which deal with the actual messaging. And there are 2 types of them, the headers frame and the data frame. The others frame are dealing either with flow control of the protocol, adjusting the Windows update, for example, or adjusting the priority, or with anything that has to do with stream management. Those streams that we saw on the single TCP connection can be opened and closed, and there are some frames that deal with this overhead of stream management. So I've mentioned that HTTP2 is a binary protocol, and that means that everything is getting packed into a binary structure. And this is the layout of a frame according to the RFC. Where the frame might change, but the headers of the frame are constant. You have the first 9 octets of a frame. The first 24-bit is an unsigned integer that would denote the length of the payload. Next, you have 1 byte or 8 bits that denote the type of the frame, if it's a headers frame, a data frame, and so on and so forth. Next, you have 8 bits for frame flags, another reserved bit, which currently has no functionality assigned to it, and the rest of the 31 bits would be a 31-bit unsigned integer for the stream ID. Let's look at an actual example. So as I've said, the first 24 bits would denote the length of the payload. The next byte or 8 bits would show that this is a headers frame, in this case, hex notation of 1. The next 8-bit, we have some flags turned in, and headers, priority, and so on and so forth. Reserved bit, the stream ID, and this is the actual frame payload. I'm sorry you can't see the gray background. Keep in mind, this is a headers frame, and I've mentioned that headers in HTTP2 are not going as in string representations. They will be compressed using HPACT and then packed into this binary formation. But I've left them on just for, so you can have a better look at what is going on. Notice that the first 4 headers are starting with a colon. These are not regular HTTP headers. HTTP2 has introduced a new concept, which is called pseudo headers. And those are the 4 headers that start with colons. I'll talk about them later. So to do a small recap, we have a single TCP connection, and on top of that connection, we have different frames, each of them allocated to different streams mapped to conversation. So a GET request using a header stream could be using a headers frame could be sent on a single stream, and the server would respond on the same stream. Meanwhile, another GET request could be sent on a different stream, and the server will respond to that. Now I have a small video here of a demonstration. You can go and search for Akamai HTTP2 demo, where we see the same image being pulled up, first in HTTP 1.1, and the second one, the same image is pulled up in version 2 of the protocol. And in this case, it was twice as fast. I think I recorded it in an internet cafe with some internet latency. But if you'll do that at your offices or back at home, you would see a speed increase of up to 4 times or 5 times more faster using the H2 methods. A few things we have to keep in mind when we're trying to analyze this protocol and inspect the content and see the conversations. First, this is a binary protocol. You can't just use Netcat and draft the traffic and see what's going on. It's not so simple. Second of all, if you add to that all implementations that I've seen are using TLS, the content is encrypted, and most of the intercepting proxies we are using currently in the web application security field, like Burp, Fiddler, still don't support H2. So if you would like to intercept a request, that becomes not so trivial. So which tools can we use to watch these conversations? Well, on the server side, I'm using the ng HTTP2 server logs. These are verbose logs, debug logs, and we'll dive into them and see exactly what goes on in these conversations. If you're on the client side, I urge you to use Chrome. Chrome has the net internals where you can actually look at all of the HTTP2 sessions you're having and see a complete verbose log of anything that goes in that session. So let's get familiarized with the logs. This is a snippet from the server log. So keep in mind, whenever you see sent or receive, this is the server side. And I just want to bring you 2 examples to see how we can read those logs. So in the first example, we see that the server is sending a settings frame over stream ID 0. And within that frame, there is a single setting, which is the max concurrent streams that the server is willing to handle in this connection. As a general settings frame, each peer of the connection can express some of its characteristics and limitations, and the other side of the connection must respect them. Next, the server receives a settings frame from the client, which has 3 different settings: the maximum size of the header size, what is the initial window size, and the maximum frame size that the client is willing to digest. This is a typical conversation. In this case, it's a GET request. I didn't include the headers because of slide real estate. But we have a headers frame sent over stream ID 15. You can see that on the right corner. This is essentially a GET request with no body payload. Next, the client sends a Windows update frame, which would increase the window size for this particular stream. This is sent over stream ID 15. You can see it up there on the corner. And there, the server would respond in a response, probably, I think this was a 404, with no content over the same stream ID. So this should give you roughly a good idea of how does an H2 conversation look like. First, the connection is established, and there are some negotiations. Now, as I've said, the RFC does allow communication over clear text, but I won't go into that because it's not really prevalent. If the communication is done over TLS, then the first stage in the TLS, when the client sends the first message of the handshake, the client hello, there is a TLS extension called ALPN, the application level protocol negotiation, in which the client states that he is willing to communicate either in H2 or in HTTP 1.1. If the server supports H2, that protocol is negotiated, and from that part on, the client and the server continue to conversate the conversation in the H2 protocol. Next, there is a settings exchange. Now, the RFC mandates both sides of the connection to send a settings frame as the first frame in every HTTP2 connection. This is mandatory. It could be an empty settings frame, but the first frame going on a new connection has to be a settings frame. And as I've mentioned, settings frame don't deal with specific stream, they deal with characteristics of the entire connection, and therefore they are always allocated with stream ID 0. So connection was established, we've exchanged some settings frame, now we can do the request. This is a full snippet of a request. As you can see, this is a GET request, which is sent in a headers frame over stream ID 1. and the server can now respond with its own server response. In this case, the response has both the headers frame and the data frame for the actual body payload of the message. So hopefully by now you have a fairly good understanding, and I'll do just a quick recap. These are the key differences between the two versions of the protocol. First protocol, I'm sorry, I don't know why you can't see the color so well. It should be orange, but I'll try to read that out to you. The first version of the protocol is a text-based protocol, where a second version is a binary protocol. Both of the protocols, either version 2 or version 1, could be transmitted over clear text TCP or over an encrypted channel. As for concurrency, first versions of the protocol use multiple TCP connections and request pipelining that was introduced in HTTP 1.1. Whereas HTTP 2 uses a single TCP connection and does request multiplexing. And last but not least, we have two new mechanisms that were introduced to the protocol: the HPAC header compression and the server push concept. And that's a neat image I saw from the Nginx documentation, where you have the first request in HTTP 1 and the binary representation of HTTP 2 request. So now that you have a fairly good understanding of H2, let's talk about passive client fingerprinting. Now, as the name suggests, this is a passive form of fingerprinting. We do not inject anything to the client. We do not execute or run anything on the client side. All we do is simply observe the behavior of the client, and from that we are trying to expose some consistent, unique behavior that would differentiate this client from other clients. Where would we look to see such behaviors? Well, we can do that in any of the layers of the communications layer. We can do that on the transport layer, looking at the TCP characteristics. We can do that in the session layer, looking at the TLS implementation. Or like we do in the H2, we can look at the application layer and actually derive this behavior from there. Who are we trying to fingerprint? I just want to make sure we are not trying to fingerprint end users. And even if we were trying to fingerprint end users, we cannot do that using passive client fingerprint. All we do is look at the software, at the way a certain client is implementing a certain protocol, and by that we can infer something on that client. Why do we do that? Well, we want to deduce something, maybe about the uptime of the client, the running OS, maybe about the running version of this particular client. And all of this information would allow us to differentiate this client from other clients. Now, specifically for HTTP 2, we are going to observe the way clients behave when they are establishing a connection. And it seems that there are a lot of consistent behaviors when you do that on HTTP 2. We are going to look into the way that the initial connection settings are being sent and the actual parameters. We are going to look at the way that clients handle flow controls and priority. And last but not least, we're going to look at the pseudo headers I've mentioned before. Now, you should, if you remember this slide, these are the 10 types of frames which are defined in the RFC. And for the fingerprinting, we are only going to use 4 of them: the settings frame, the Windows update frame, priority, and the pseudo headers. So let's deep dive into them. First one is the settings frame. Well, as I've mentioned, the settings frame should convey configuration parameters from the entire connection, and they must always be sent by both endpoints of the connection, at the start of any connection. Now, we would actually look at the default parameters and harvest them for our fingerprint. In general, the RFC defines 6 types of parameters that can be used, and each of them is assigned with a unique ID. And some of them deal with server push, the frame size, the headers table. And we would look at the ones which are being sent. This is an example for Firefox 55, which sends upon any new connection these exact settings. It would send exactly 3 settings, each of them with those exact parameters. So we just look at that and we harvest that into our fingerprint. Safari, for example, would send different set of parameters, and for each parameter, it would have a different type of values. And I've added some examples for Edge and for Chrome. And taking all of these settings and putting them in one table was the first step towards the fingerprint. You can start I'm sorry, you don't see that very well, but you can see all of those 6 parameters here. And you can see that for different clients, like for Firefox 52 on Android 6, sends different parameters than Android, my Chrome on my Android Pixel XL. So we started plotting out this table, and next we moved on into forging a fingerprint. So for the settings part, we take the parameter ID and the value, and when we start to concatenate them. This is for Edge. The same example can be made for Firefox. We take those 3 parameters and parameters ID, and we start to concatenate them. But that wasn't enough. That did not give us enough entropy to differentiate and distinguish between a large number of clients. So we moved on to the Windows Update. Now, apparently, some of the clients, and a lot of them, when establishing a new connection, does not only send a settings frame, they also send a Windows Update frame. And the value which is included within that frame is quite consistent. Now, as I've mentioned, the Windows Update frame deals with flow control. There is an initial Windows which is could be set implicitly or explicitly. There is a default size mentioned in the RFC, and clients can use a settings frame to set the initial Windows size. So we take the value from the Windows Update frame and we add it to our fingerprint. Now, if there was no value sent, we would just put 0. So the first part of the fingerprint would be composed of the settings frame. The second part would be composed of the value of the Windows increment size in the Windows Update frame. And if there was no value or no frame sent, we would add 0 to it. Still not enough entropy. So we looked further and we kept the research, and we found that we can use the priority frame mechanism. And this is actually quite an interesting mechanism in the protocol. Now, HTTP2 allows to set a dependency tree between frames. I'm sorry you cannot see everything here. Well, if you look at the left side from your perspective of the frame, you see 5 streams, stream D, E, C, A, and B, where stream E and C are dependent on stream D, and stream A and B are dependent on stream C. Now, each parent stream, the stream on which others dependent is called the parent stream, and the streams below it are called dependent stream. So what does that mean? The RFC allows the client to express its preferences of how the server should allocate resources in case it doesn't have enough resource to send all of the data. Now, this is just a suggestion. The server does not have to comply to the client preferences, but never the same, the client can express those preferences. And each of these streams have weights below them. For example, in this example, the client is telling the server, listen, if you have some kind of a resource limitations, please use your resources first on stream D. Once you are done with D, use your resources for stream E and C, and each of them has a weight of 8. That means that the resources between them should be split 50% and 50%. Once you're done with stream C, please allocate your resources to stream A and B. And if the weights are 12 and 4, we can surmise that the resources should be distributed as 75% of the resources should go to stream A, and 4% and 25% should go to stream B. So we found out that some of the clients actually does not only send the settings frame and the Windows Update frame, but immediately after that, they start sending priority frames. And this is a live example for Firefox. Firefox would send a settings frame, it would set a Windows Update frame, and right after that, 5 or 6 priority frames. And can anyone think why would Firefox do that? Why would he create this dependency tree? Well, essentially, there are 3 lanes. He has the high priority frame over there in stream number 3. He has normal priority, stream number 5, and low priority, stream number 7. So we collect all of the data, which is sent in the priority stream, the dependent tree, the weights, and another exclusivity bit. And we've actually looked into this is a snippet from the comments in the source code of Firefox, and this is actually hard-coded. The behavior which are depicted up until now, the sending of settings frame, next the sending of a Windows update frame, and the sending of the priority frames, and the values would be hard-coded. So those are consistent and would differentiate Firefox from other browsers that don't behave in that manner. So now we have a small recap. This is all of the 3 elements we've picked up until now. And you can start seeing that we can now differentiate between a Chrome browser on Mac OS X, between a request sent by OKHTTP library, a Java library, or the curl library, curl client, or the ng HTTP2 client. Each of them has a different signature, and this is awesome. But we are almost there. One last element. This was really nice, but it did not generate enough entropy. We needed another component that would help us further distinguish between clients, because there were a lot of clients at that stage that still had similar characteristics. So we've introduced the pseudo headers. Now, what are the pseudo headers? The RFC defines a closed set of pseudo headers. 1 for the response, and 4 for each request. Now, if you think about it in terms of HTTP 1.1, some of the headers, the data in the headers is the data that was included in the request line. You can see the method, the get, the path, the resource which is requested. The authority used to be sent in the prior versions of the protocol in the host header, and there was we added the scheme. Those are the 4 pseudo headers. There's a closed list. No one can add to it. If someone would actually try to add to these headers, the protocol would mandate that it would be considered as a protocol error and the connection would be broken. So what was interesting about these headers, and of course from the client perspective, we are only interested in the request pseudo headers, is that if you look at different clients, each of them send those headers in a different order. Like Chrome would send method, authority, scheme, and path, whereas Safari would do method, scheme, path, and authority. So if you look at that, you can once again use that and differentiate, I don't know, the Go HTTP client from the JD HTTP client. Looking into Chrome source code actually validates the assumption that this is consistent. The structure in which the headers, the pseudo headers are sent is a constant, and it would not change for Chrome. So now we get to the final fingerprint. We've reviewed all of the elements. The first element would be collecting the settings parameters, the IDs and the parameter values. Next, we would collect the Windows update. Third, we would look at the priority frame. And if there is no Windows update or priority, we would actually plant a 0 there. And the fourth element is encoding those 4 pseudo headers and looking at the order in which they appear. Now, the fourth element is a bit different from the previous one because we actually have to wait for the first response. For the first request to collect the pseudo headers. But initially, every connection is usually being created in order to send requests. So this is the only difference, the key difference between the fourth element and the other 3. So what are the use cases? Can any of you think about nice use cases for these fingerprints? I know it's 3:30, it's hard. Well, there are several use cases for this. First of all is positive security. If someone, if a request is coming from a browser which asserts to be a certain version of Chrome associated with a certain operating system, you can validate that. You can look at the fingerprint and see if it matches the fingerprint that we have recorded for this particular version and for this particular operating system. That would allow us to detect browser impersonator. We can detect search engine impersonators. We can detect all sorts of other tools. And the last thing we can do is that if we see an IP address from which a very large amount of distinct fingerprints are originating from, and these fingerprints are attributed to different operating systems and different versions and we can try and use that data to surmise that this is some kind of a shared IP. It could be a corporate gateway, and if the amounts are really big, it could be an anonymous proxy or a VPN. So for any of you who is interested in those capabilities, it can be used for detection of such IPs as well. Now, the last comment I included is very important for everyone who's doing fingerprinting. It is always, to get optimal results, it is always best to combine fingerprinting from different layers. If you can't fingerprint everything, look at the session layer, look at the application layer, look at the transport layer. Combine the TCP with the HTTP versioning. And if you're doing some active client fingerprinting, I don't know, you're doing some JavaScript fingerprinting, combine that as well. So you get the whole picture for each client, and you'll have a lot more to go by in differentiating those clients. Well, I thought that every lecture about H2 in Black Hat should at least address the threat landscape for H2. And as I've said, in Akamai, we see huge amounts of traffics. And a lot of this traffic is attack traffic, and we can differentiate and plot a visualization of what would the threat landscape for H2 look like. And before making this presentation and the research, I've gone and queried our system and our logs to see how does the threat landscape for H2 looks like. And there you have it. It's a complete desert. Actually, there's not a lot of attacks over H2, especially if you compare that to HTTP1, and that got me thinking, why is that the case? Why should that be the case? I mean, it's a faster protocol, it's a new protocol, it has been around for almost 2 years now. Why don't we see attacks for the H2 protocol? Well, there are several reasons. First of all, most security tools, the tools of the trade that most of you know, still does not support H2. You have some decent names up there. I don't know if you can see it. Burp, Fiddler doesn't support H2. Zap, OWASP Zap, scanners like Akinetic scanners, NetSparker, AppScan don't support H2. Attack tools you have up there, which are usually used for penetration testing and for other purposes, still do not support H2. You have SQL Map, Hydra, Sentry MBA for credential abuse. All of these does not support H2. Why is that so? First of all, there's not enough incentive for attackers to do that. Most of the servers, if not all of the servers that I've encountered, don't support solely H2. They have a fallback to H1 to be compatible with most browsers in the internet. And if you take in the fact that most HTTP libraries are not so common, I mean, all of the large programming languages do have them, but they are not so mature and so easy to use as the ones you have in the HTTP1 world. So essentially taking the cost of taking your existing code and porting it to work with this new binary protocol just exceeds the gain. If at the end of the day, all you want to do is take your payload and make sure that the application gets it, you can use HTTP1 for that. The messaging layer is not really important. And though you can gain some performance, the cost of porting the code would be quite big. I would like to mention that in 2016, there were some server implementation flaws that were found by researchers, I think from Imperva. Those are not flaws in the protocol. No flaws has been found for the H2 protocol. Those are flaws that were found in the way that certain servers implement the protocol, and more specifically, the way they handle stream management and the header compressions. So what are my key takeaways from you guys? I hope that by now you have a fairly good understanding of how HTTP2 works, and more specifically of its key elements that we've covered and the key differences between prior versions of the protocol. I hope that by now you should have a good understanding of what passive client fingerprinting is, and more specifically of the fingerprint we proposed for H2. And last but not least, you are now well aware of the lack of threat landscape, current landscape in HTTP2. Questions, please. Yeah. Just a sec. Oh, there's a mic. Okay, she'll get you. Yeah.
Yeah. Can you hear me? There we go. So you mentioned that clients can opt out of the sort of proactive push from a server. Do you have any idea of what percentage of them bother to do that?
I don't have that the statistics ready made. I don't want to throw you a wrong number. I don't want to throw you no.
Okay.
There are quite a few that does take advantage of that, and a lot that don't. If you remember the slide I think about Safari is opting out of it at every initial communication, and that's a large portion of usage that won't. A lot of users from these browsers won't be able to enjoy that currently.
Okay, and presumably there's a performance impact associated with opting out, is there? Because you said H2 is about 4 times faster normally. I'm guessing if the servers can't sort of push stuff they expect you to need, that's going to drop off pretty significantly. Yeah,
the whole point of doing a server push is to improve your performance. So do you mean performance drop in terms of the server performance?
Yeah. So if I were browsing and I opted out of server push, is there still going to be a performance gain at the end of the day from using HTTP2, or does it become sort of pointless at that point?
Absolutely. Just the mere fact that you're using now a single TCP connection and data like headers is being compressed and sent in a, you don't have a connection which is waiting for a response to send another request. Everything is multiplexed and compressed. Even without the server push, you will have a significant performance improvements.
Okay, thanks.
Thanks for the talk.
Thank you.
Is it working?
Yeah.
I have a question regarding basic understanding of HTTP2 and server push.
Yes.
Which is if the server wants to take advantage of the server push and pushing, for example, CSS and JavaScript contents to the client, doesn't the server have to parse the HTML document in order to do that?
Well, yes, absolutely yes. And this is up to the server to know which resources to push. And it depends on the server implementation, but the answer is yes.
So parsing is needed for that?
Yeah, actually. It would have to be done beforehand so the server would know what to push and not just push everything.
Okay, thank you.
But it's a mechanism which is enabled. So the RFC does not exactly tell you how to implement that part. It just gives you the actual functionality within the protocol, and it's up to you as a server implementer to decide how you do that.
Do you think that H2 features can be used to fingerprint also servers, web server, or?
This is an interesting question. We are not in the business of fingerprinting servers, but absolutely. Absolutely, because, for example, if you know that some servers never take any advantage of the server push, you can look at the way that the server actually, the settings that is sent, because both sides of the connections should exchange setting streams, so you can fingerprint the server back as well. You can look at the default values, you can look at the way that the server is managing streams.
Mm-hmm. Do you have some statistics, maybe some number, about how many servers does implement H2?
I told you from what we've seen, I don't know in terms of servers, but we've seen more than, I don't know, the number was 15,700 different hosts which support H2. I don't know how to translate that into actual how much server versions and implementations, but there's a lot of adoption. It's not a negligent number.
Okay, thank you very much.
Was someone back there? Oh, sorry.
Hello. You mentioned earlier on in your talk about trying to discover client uptime. Was that something you managed to get out of the fingerprinting? No,
this is a feature that you can get from TCP fingerprinting. And certain operating systems, you can deduce things about the uptime of a certain client, not in the HTTP tooler.
Hi.
Hi.
Are you fingerprinting the traffic just for the purpose of this talk, or do you routinely fingerprint everything that goes through Akamai's network?
Well, this could be like something which is part of a certain product. Like if a customer would want some of our, I'll give a concrete example. If a customer wants to leverage a product which is dealing with mitigation of bot traffic, one of the way to identify bots from humans without, doing a collection of biometric attributes or things like that, which we currently don't do, is actually look at the protocol fingerprinting. As I've said, this is absolutely passive. We do not prod into the client. We only observe the way that the client behaves. And it does not correlate to any end users because all it says is how this particular piece of software is implementing this particular protocol. That's it. And keep in mind that sophisticated attackers could fool you. I mean, if you are writing your own client for HTTP2, you can decide to randomize the values for the Windows increment. You can do all sorts of stuff, but at the end of the day, when you are dealing with a big platform and the big numbers that we see at Akamai, you would stand out even more because all of the Chromes, if you would try to pass as a legit browsers for a certain version of Firefox for a certain operating systems, the big numbers of this particular software, you would stand out trying to randomize all kinds of other parameters because you would be the only one doing that. Yeah. I'm sorry, I didn't answer just one bit of your question. There is some performance hit in terms of running fingerprinting and some cost associated to it. So we don't do it for all of the traffic going over Akamai's implementations.
Hi.
Hi.
What do you think about the Quick protocol used recently by Google? Quick protocol?
Quick, okay, yeah. Well, Quick is, first of all, is a protocol based on UDP. And it's an exciting new protocol. It's not so new, but I think it's a great protocol because in today's internet, reliability is not such an issue, and it's very fast. UDP is very fast. It's implemented its own set of cryptography, which is very interesting. It's an interesting way. I think it's a very interesting subject for exploration. If the question was in terms of fingerprinting, it's absolutely a target for research.
It was more like, do you see Quick as something that could compete with H2?
Absolutely. Absolutely. It's hard to defeat the protocol which runs over UDP in terms of performance. Okay. Thank you very much for taking the time to attend this presentation. Thank you.